Good morning, students. So this is the 25th lecture in the series of electric and hybrid vehicles. We have started the module number 4. We had started it yesterday. And yesterday we have seen the initial topics in this. So there are two parts in this module number 4. So first part is the electric vehicle and second part is the hybrid electric vehicles. So in the first part of electric vehicles, actually there are some three, four, or actually there are four topics actually. So first was the configuration of EV, that is the configuration of electric vehicles. We have seen how the primitive electric vehicle was converted to in-wheel electric vehicle. So there were six models, there were six modules that we have discussed yesterday. That is the evolution of electric vehicle from the initial primitive electric vehicle to the modern day in-wheel electric vehicle. Then there was the performance parameter. So under performance parameter, there are three factors. First one is the traction motor characteristic. We have seen it yesterday, we have completed. Second topic was tractive effort and transmission requirement. So this is going to be our first topic today. After that, there is the vehicle performance. Now, one thing I'd like to tell you, all these topics we have actually seen in the initial module. That is traction motor characteristic, tractive effort, transmission requirement, vehicle performance. All these things are actually seen in the module number 1. We have seen what is the aerodynamic drag, what is the gradability, what is the acceleration formula, what is base speed. All these things we have seen. So here it is going to be a kind of a recap. So we have seen all this thing in detail in the module number 1. Here it will be a recap of all those things once again. Hence, I have not given much time on all these three topics. That is the traction motor characteristic, tractive effort, and vehicle performance. So I told you yesterday that it can be two questions. That is, first question can be configuration of EV. So there are six configurations that you have to explain. So it can be a 10-mark question. Then performance of EV. So you have to explain all these three topics, that is traction motor, tractive effort, and vehicle performance. So tractive effort, transmission requirement, and vehicle performance we will do today. Then there is coming tractive effort for normal driving. So whatever tractive effort we have discussed previously, what happens in normal driving? So there are mainly two cases. One is stretched for performance, like we are climbing a hill. At the time, huge amount of power is being required and all those things. So those are special cases. But tractive effort in normal driving. Now normal driving can be three, four different types. So what are the three, four different types? Like one is driving through a highway. Another can be driving inside a city. So too much of start stop. All those things are happening. So normal driving, not hill driving. Okay. So either highway driving or inside city driving. All these things are called as normal driving. So in that case, what is the vehicle performance? So that is the tractive effort in normal driving. A very important topic we will see. And as per the explained in the book, we will see four different driving cases, and we will see what is the gear arrangement most of the time when the vehicle is running through the city or running through the highway, all those things. So very interesting topic, this one, tractive effort in normal driving. Those who know driving, they can correlate with it very easily. Okay, and final one is the energy consumption. So with this, we will finish the first half of module number 4. So I told you that this module number 4 and module number 5 are not as exhaustive as the first three modules. So many things we have studied in first three modules, but this modules 4 and 5 are more application oriented, and they are little less exhaustive. So let us go enter the second topic in the performance. So first topic of traction motor characteristic we have completed yesterday. We have seen there the characteristic of maximum torque versus maximum initial torque versus maximum power graph. All those things we have seen yesterday. Now tractive effort and transmission requirement. So this is an important characteristic we are going to see today. Let us see. So what is meant by tractive effort? Tractive effort is nothing but whatever power we are giving for the traction job, for the driving the vehicle forward, that is called as tractive effort. So how much effort we are doing and how much output we are getting from that. So this is going to be a study here. So it is said that tractive effort developed by a traction motor okay, on driven wheels and the vehicle speed are given by, so there is a formula, ft is equal to tm ig I0 eta t rd. So yesterday we had discussed this slide, we have known what is tm. So tm is nothing but the torque produced by the motor. Ig and I0, they are the gear arrangement, and they are the gear ratios and all, they are constants. Eta t is the efficiency, so it is given here tm. So in this case tm is the motor torque. So whatever motor we are using in the electric vehicle to drive the vehicle, so that motor is producing the motor torque. And actually we are finding the tractive force. So this force is given in newton, tm is given in newton meter. Nm is actually the motor speed, this is given in rpm. V is the vehicle speed, which is given in meter per second. And tm, actually I told you, this is the motor torque output. Ig is the gear ratio of the transmission. I0 is the gear ratio of the final drive. So from the engine to the final drive, that means to the drive wheel and all. So there is a lot of step-by-step conversion or step-by-step transmission of power. So every step there is some kind of reduction in the power or energy transmitted, because the power or energy is getting transmitted by means of gears. Okay, so whenever there are gears, there are certain ratio, either power increment or decrement, torque increment or decrement, all those things are there. So this ig I0, it depends on which gear the vehicle is in, and these are kind of a constant factors. Eta t is the efficiency of the whole drive line from the motor to the drive wheel, that means from the power generation up to the power dissipation, how much is the efficiency of that. So we'll find whether it is 70%, 90%, we'll check. Rd is the radius of the driving wheel. So these are the variables which are used to find out how much is the force generated by the vehicle and how much is the speed of the vehicle. And while finding the vehicle speed, we have to see what is the motor speed. So motor which is running the vehicle, its speed is given in nm radian per second, and rd is actually the radius of the driven wheel. So this was the slide explained last yesterday, and we are finding there are certain inferences coming out from it. It is saying that the use of multi-gear or single gear transmission. So next we are going to see three graphs, that is single gear, double gear and triple gear, how the tractive force is being different in all these three cases. So the use of multi-gear or single gear transmission depends mostly on the motor speed torque characteristic. So it depends on what the driver wants and what kind of speed torque characteristic we are receiving from the motor. Depending on that, we use either single gear or multi-gear system. At a given rated motor power, if the motor has a long constant power region, so yesterday we had seen x is equal to 2, x is equal to 4, x is equal to 6, where x is the ratio of maximum motor speed divided by the base motor speed. So base motor speed for any drivetrain is predefined or pre-designed, and maximum speed also is predefined or pre-designed. So this for every gear, how much is the value of x? So it is the ratio of maximum speed divided by the base speed. So for every gear train, the base speed is constant. So the graphs I will show you just now. So we have found that for x is equal to 2, we are finding that constant torque region is very small and constant power region is very wide. So at a given rated motor speed, if the motor has a long constant power region, that means x value less, a single gear transmission would be sufficient for a high tractive effort or low speed. That means whenever it's a single gear system, in that case the tractive effort will be high and speed will be low. Okay, so it is like that activa and all those things, we cannot increase speed too much. Okay, like that. So otherwise a multi-gear or more than 2 gear transmission has to be used. So what is the advantage and disadvantage of single gear, multi-gear, we will see here. Now here these graphs were there which I wanted to explain. Yesterday I started it, but I could not explain it. So these are the things you are supposed to observe below the graph. What is this? So tractive effort versus vehicle speed. So y-axis is the tractive effort, x-axis is the vehicle speed. That means I am increasing the value of the vehicle speed, and with respect to that, how much is the force produced by the vehicle. So this is the force produced by the vehicle, that is the tractive effort, ft. This is in kilonewton or newton. And how much is this vehicle speed? So speed versus force, this is the characteristic which is called as tractive effort and transmission requirement. Now here you are finding that this is the first region. This is the first region where base speed is vb. So here you are finding that there is another curve. So there are two curves actually. Actually there are four curves, I'm sorry. So first one is this AB. Okay, so this is the constant torque region, and here this is the constant power region. So this is also called as constant power, means in this case the torque is actually reducing and the power is actually increasing. So power is increasing like this, and then power is staying constant. So yesterday in the traction system we have seen what is the constant power graph, but here the torque is reducing, power is constant, that means speed is increasing actually, because I told you that uh, torque multiplied by speed, that is equal to power. So in this case power is constant, okay, torque is reducing, that means speed is increasing. And how is the speed increasing? Speed is increasing like this. So this is given by the graph here. So this is the speed increment graph where you are finding that. So below here initial speed is very less because torque is very high. So in this position the car is at first gear, then it increases second gear. So as we are increasing the gear, at that time we are increasing the speed actually. So exactly at this point what we are finding is ft minus fr minus fw. So how much is the actual tractive power? So we are finding that there are two losses. Fr is the so loss because of that radius and friction and all those things we have found. Fw is the loss because of windage. So ft is the power energy we are generating, and fr and fw are the losses. So how much is actually the power or energy that is driving the vehicle? That is given by ft minus fr minus fw. So at this point, at this much speed, you can say how much is the speed? Around 90 kilometer per hour. In this case, we are finding how much is the actual energy given by the power to drive the vehicle. So this graph is very important. Please give some time to understand this graph. Okay, and then this is actually the increasing in the ft, that is the tractive power with respect to speed. And wherever this tractive power versus speed, this is cutting this graph. So this is with respect to gear, how much is the speed changing. So wherever this constant torque graph and this power energy graph, they cut each other exactly at this point. So this is the energy graph. Energy is increasing with respect to speed. This is the torque graph. So torque is initially constant, then the torque is coming below. So there's a hyperbolic kind of a decrement. So wherever this constant torque and tractive effort, they are cutting each other, this point is called as a maximum speed. And for this vehicle maximum speed we are finding around 190 kilometer per hour, is like this. And this height is actually very important because this is the maximum speed, and maximum speed divided by this 30. So in this case maximum speed is around 180 190, so around 180 you can take. And how much is the vb? So vb in this case you are finding that base speed at first gear. So this is the first gear thing. So abc, so a b and c, okay, so a b and c, a b and c, this is the first gear. So when the vehicle is in the first gear, up to speed 30 kilometer per hour, we are keeping the first gear, then we are changing the gear. As soon as we are changing the gear, the torque is reducing but the speed is increasing. So exactly at c point, how much is the torque? Torque is this much, so torque is around so this is the c, okay, so torque has reduced. Initial torque is very high, so here the torque has reduced but the speed has increased. You can find out speed has increased almost up to 60 kilometer per hour. So this graph reading is very much important. So ABC is the first gear operation. So for that VB is around 30 kilometer per hour. Now DEF. So this is DEF. This is the second gear. So as soon as you are doing the second gear, your tractive force is actually reducing. Okay. So in this case, tractive force previously it was around 6.6. You can say in the first gear. So tractive power was more, FT was more, torque was more. Now as soon as the second gear, what you are finding is the tractive force is reducing, so it is around 4.3. So from 6.6 it is reducing to 4.3, but the base speed has increased, so you can find the base speed is almost 50 kilometer per hour. So this thing you have to join, this e point you have to bring to the ground. So in that case it will be around 50 kilometer per hour. So as you are increasing the gear, at that time the VB is increasing. So here it is around 50 or 45, and here it is 180. So 180 by 45, we are getting as 4. Numerical will be asked on this. So please prepare this graphs well. How to read this graph, this you should understand very well. So here maximum speed is around 180 you are finding, or 190, and here for second gear VB is around 45. So this 190 or 180 divided by 45, we are finding that for this DEF second gear, we are finding X is equal to around 4. That is 180 by 45. Just sit with this graph once and see my previous slide also. It is already uploaded. From there you will find how much is the X value, and X value actually decides which gear is it and how much is the tractive force and all those things. Finally, third gear, and this is mistake I told you, GFH it should be. So G, F, and H it should be. So this is the torque characteristic with respect to increasing speed. And this is the third gear. So in the third gear, as we are increasing the gear, the torque is actually reducing, but base speed VB is increasing. So this is VB for first torque, VB for second torque is around 45, VB for third gear is around 100 kilometer per hour, and this is almost 200. So 200 by 100, it is almost x is equal to 2. So this is the region where x is equal to 2. The top is the region where x is equal to 6, and medium is the region where x is equal to 4. So as you are increasing the value of x, actually you are increasing the gear. The power is the same, but torque is reducing, speed is increasing. So this is the graph you have to understand, and this is a what is this graph? This is said that this is a tractive effort. So these are all the tractive efforts. This is the tractive effort, and this is also the tractive effort which is increasing with respect to increasing speed. Torque is reducing, power is constant outside this region. So tractive effort versus vehicle speed with a tractive traction motor of x is equal to 2. Okay, so initially VB is this, x is equal to 6, so it is starting. It's a 3-gear transmission. Okay, so there's a 3-gear transmission because you're finding, and maximum. So how can we say x is equal to 2? X is equal to 2 is because highest gear, whatever is the highest gear, third gear is the highest gear, and what is the VB there? So at VB, at highest gear is 100, and this is maximum speed almost 200. So this x is actually calculated with respect to the highest gear VB. So in this case, highest gear VB is 100 and maximum speed is around 200. So 200 divided by 100 is equal to value of 2. So this is x is equal to 2. So x is equal to 2 means it's a 3-gear system. So figure shows the tractive effort of EV along with the vehicle speed with a traction motor of x is equal to 2. So this x is equal to 2 defines motor. So last day we have discussed SRM. SRM can give us x value greater than 6. Okay, and we have found induction motor or maybe BLDC motor was having kind of traction value x is equal to 4 or something. What is meant by x? X is nothing but depends on the motor characteristics. Likewise, okay, the first gear covers the speed region ABC, second gear covers speed region DEF, that is DEF, and third gear covers the speed region GFH. So GFH, and in the book of Asani it is given wrong, it is given GEH, so make it GFH. So this graph you have to understand very thoroughly. Next we are going to see the same kind of graph, but we are finding that there are only two regions. Okay, there are only two regions, and it is said that tractive effort versus vehicle speed with a traction motor of x is equal to 4. Why x is equal to 4? Because in this case highest gear is second gear. You find that there is no third gear. Okay, so first gear characteristic is same, second gear characteristic is DE, and this is F. So this is DEF is the second gear characteristic. First gear characteristic is ABC, and this is the base speed. So you have to just connect this E to the ground, and you will be finding that this is around 45. Okay, so 45 kilometer per hour is the base speed. That means up to 45 kilometer per hour, the torque is constant. That means we are at the initial phase of the vehicle. And after 45 kilometer per hour, we are changing, we might think of changing the gear, but we cannot change it because in this case, the second gear is maximum. Okay, so after that, if we are increasing speed, in the keeping the car in second gear, if you are trying to increase the speed, in that case we are finding that the tractive effort has to be more, and wherever this speed and tractive effort characteristic is cutting the torque characteristic at this point, this is called as the maximum speed, and this maximum speed is around 180, and this E point if you bring to the ground it is 45. So this 180 divided by 45 is equal to 4. That is nothing but the x value. So I told you that x value is calculated for VB for the highest gear. Previous case, the highest gear was third gear. In this case, VB was 100. Okay, so up to 100 almost, the initial torque was constant. That's why we took VB as 100. For first gear, the VB is around 30. So for first gear, if you ask me how much is the x, it is 180 by 30 is equal to 6. For second gear, it is around 45. How much is the x value? It is 180 by 45, that is equal to 4. But we will not consider that because in this case there are 3 gears, and highest gear is having VB as 100. So that's why this system is having x is equal to 2. Like this we will talk. This system is having x is equal to 4, and this is actually the increment in the rolling resistance and aerodynamic drag. Okay, so as rolling resistance and aerodynamic drag is increasing, what we find is net tractive effort that is actually reducing. Okay, so there are two things. One is tractive effort, how much FT you are putting, so that is actually increasing. But net tractive effort, so that is FT minus all the losses, because this is a graph where losses are increasing. Okay, in the previous graph also, this is a graph where losses are increasing. So as losses are increasing, net tractive effort, that is FT minus FR minus FW, that is actually reducing. So that's why the torque is also reducing, but the vehicle speed is increasing and power is remaining constant. So this is the second system. So whenever tractive effort and transmission requirement is asked, this also can be a 10-mark question. You have to explain all these things with respect to three graphs. So this is the second graph where x is equal to 4, because base speed is 45 in this case, and it's a two-gear transmission. So highest gear is the second gear. And there's a last characteristic. There is the single gear characteristic. So here there is only one gear you are finding, that is the first gear. Okay, so in this case it is written here, single gear transmission motor speed ratio is equal to x is equal to 6. Why 6? Because you can see here the rolling resistance and aerodynamic drag, they are increasing with respect to the increment in the speed. There is only one speed, there is only one gear, so this is the VB. So initially up to 30 kilometer per hour we will find that the torque is kind of a constant. So in this case the torque is not written, so this is constant torque or constant power. So same thing should be written here, this is constant torque, and here it should be constant power. So torque is constant almost up to 30 kilometer per hour, and after that if you are increasing speed, in that case your torque will reduce. So this is the way the tractive effort is reducing, because after this the aerodynamic drag and the rolling resistance, they are increasing. Okay, so there are two things, one is tractive effort and another is effective tractive effort. So this is that effective tractive effort is reducing. So here you're finding that figure shows the tractive effort with a traction motor x is equal to 6. So kind of motor we can use here is SRM, that is switched reluctance motor, and a single gear transmission. So this is the kind of a thing which is there in Activa. So it's a single gear transmission, there is no change of gear possible. So if you are try to increasing the speed of the vehicle too much, in that case you'll be finding torque is less. So in higher speed, if you are trying to go through an incline or something, the vehicle might not go up, because as you are increasing speed, in that case the vehicle torque is actually reducing. So these three designs have the same tractive effort versus vehicle speed profile. Therefore, the vehicles will have the same acceleration and gradability performance. So there are three performance things. What we will find, one is the how much is the power, how much is the speed, acceleration, and how much is the gradability. So this three diagrams here, you are finding that this is a x is equal to 6 and one gear transmission, because we are finding that there is only one flat region. Okay, this flat region is actually the constant torque region. Okay, so there is only one flat region, only one gear, only one VB of 30 what is that, 30 kilometer per hour, this case. So all these three cases, this is the third, this is the second case 2-gear transmission, this is the first case 3-gear transmission. So all these three characteristics is having the same constant and same fall. Okay, hence they are saying as that acceleration and gradability performance for all these three cases will be same. But the first case was 3-gear system, second case was 2-gear system, and this is the last case, it is the single gear system. So tractive effort with respect to different multi-gear system, if this question is asked, these three graphs with their explanation you have to show. And here you have to show this is the constant torque and here is the constant power. And this you should understand what is the effective tractive effort, ft minus fr minus fw, and as speed is increasing, fr and fw they are increasing, and as fr and fw they are increasing, net tractive effort is actually reducing. That's why you can find that this graph is increasing and this net tractive effort graph is decreasing. Next we are coming to another important thing. So there are 2-3 slides on this, and all whatever we are going to see here we have already seen this. Okay, so there are 3 parameters for vehicle performance. So here we are talking about EV performance. There are 3 things. First one is maximum speed, second one is gradability. So gradability is nothing but the height of the car divided by that base of the car. So I by h alpha we found it. First one is the maximum speed and last one is acceleration. So what all formulas we are going to use, that is also we have already seen. So let us see these 2-3 slides. So basic vehicle performance includes maximum cruising speed, gradability and acceleration. So maximum cruising speed of a vehicle can be easily found by the intersection point of the tractive effort curve which is falling with the resistance curve. So you find here this is the tractive effort curve and this is the resistance curve which is increasing. So their intersection point is nothing but the maximum speed. So the resistance curve is actually rolling resistance plus aerodynamic drag. So rolling resistance is there in the vehicle wheel, and aerodynamic drag is because of its shape, whatever opposition the air is given on the vehicle. So that is increasing actually, because as a vehicle speed increases, aerodynamic drag also will increase. Okay, so intersection of these two graph is nothing but your maximum speed. So if you remember here also in this graph, maximum speed is shown here almost like 180. Okay, now what is the formula? So such an intersection point does not exist in some designs. So if it is existing in some design, it's okay, but if it is not existing, then there is a formula. So how much is the Vmax? So in that case, if that graph is not existing, which usually uses a larger traction motor or a larger gear ratio, in this case, whenever this kind of characteristic is not found directly, in that case, what we are doing is we are finding Vmax formula. So what is the Vmax? Pi nm. Nm nothing but the rotation of the motor. How much is the maximum rotation of the motor? So max, Nm max. So how much is the maximum rotation? Rd is the tire resistance, tire radius. We have found 30. I0, Ig is the that gear transmission ratio, Ig min and I0. So I0, Ig min, Rd, they are vehicle constants. And Nm max is actually the speed of the rotational speed of the motor, that is in RPM. Okay, and this is not vehicle speed. Vehicle speed is given by Vmax. So what we find is Vmax is directly proportional to Nm max. That means how fast the motor inside the vehicle rotating, the vehicle speed will be directly proportional to it. So this is evident because the motor itself is driving the vehicle. So if the vehicle motor rotates with a higher speed, means vehicle also will go forward with a higher speed. So what we find is Nm max and Vmax, they are directly proportional. And where Nm max is the allowed maximum RPM of the traction motor, Ig mean is the minimum gear ratio of the transmission for highest gear. So whenever gear is at highest, that means at 5, at that time Ig will be the minimum value. Okay, so this is the gear ratio. So for smaller gear, Ig is higher value. For higher gear, Ig is a lower value. Likewise, so this is about a maximum speed. So there are two ways of calculating maximum speed. This also can be asked as a question, that what are the two ways of finding maximum speed. So first you have to explain, you have to draw this kind of a graph, and you have to say that from this tractive effort versus vehicle speed, we can find out how much is the maximum speed. So wherever this losses, that is rolling resistance and aerodynamic drag, this loss curve is cutting the tractive effort curve, there we are finding that speed is maximum. So this is the first method. But if that graph is not available, in that case what we have to use is a direct proportional between the rotational speed of the motor and the vehicle speed. So what we find is Nm max is directly proportional to Vmax. And what is the relationship? It is a function of Rd, Ig min, I0, Ig0 and all those things. Now next is what we are finding is another performance parameter, that is called as gradability. So gradability is nothing but that I, okay, whatever I is there or sin alpha was there, we had found out in case of any vehicle. So gradability is determined by the net tractive effort. So net tractive effort, Ft net, is given by Ft minus Fr minus Fw. So that's what I was talking about in the previous graph. If you are finding here, so one is tractive effort, another is net tractive effort. So this is actually the net tractive effort. It is Ft tractive effort generated minus Fr minus Fw. So resistance is subtracted from the actual tractive effort to find the net tractive effort. So that much we are finding. So as shown in previous three figures, at mid and high speed, the gradability is smaller than the gradability at lower speed. The maximum grade that the vehicle can overcome at the given speed can be calculated by. So maximum grade means maximum inclination that the vehicle can overcome is given by I Ft net by mg. So this is I actually is equal to the vehicle height divided by vehicle base. So that is another interpretation of this. Okay, so gradability is something which is determined by the net tractive effort of the vehicle, and net tractive effort can be given as the tractive effort Ft minus Fr minus Fw. So tractive effort is nothing but the force which is generated by the vehicle. So in previous three figures, it was defined how to find out the Ft net. So it was shown in the previous figure. So at mid and high speeds, the gradability is smaller than the gradability at lower speed. So the maximum grade that can vehicle can overcome at any given speed can be calculated by how much height or how much grade the vehicle can overcome. That means how much height it can go above. Okay, so this is given by ft net by m into g. So m is the mass, g is the 9.81, that value we know. So this is ft minus fr plus fw. So this is ft net by mg, and here ft is the tractive effort of the driven wheels, fr is the tire rolling resistance, fw is the aerodynamic drag. All those things we know. So however, at the lower speed the gradability is much larger. Okay, so we know all these things actually, so there is nothing different. So gradability calculation with higher accuracy. So in this formula actually previously we are not considering few things, but if you want higher accuracy, sine alpha. So sine of alpha, alpha is nothing but that h by l. H is nothing but the height of the vehicle, l is nothing but the distance between the two tires, so or length of the vehicle, as we say. So it can be given by sine alpha. So d minus fr root under of 1 minus g square. So fr is the rolling resistance we know, and what is d? So d is a new factor. It is ft minus fw by mg. So in sine alpha, so any one parameter you can use to find gradability. So this is also another vehicle performance parameter. So if you're using this more accurate formula, in that case you have to find out d first, and d is nothing but ft minus fw. So in this case fr is not taken because fr is coming afterward. So d is ft minus fw minus, so this is nothing but the whole capital fr, where small fr is a function. Okay, so fr is the tire rolling resistance, small fr, and capital fr is the rolling resistance based loss. Okay, so this is the difference between capital fr and small fr. So likewise, we can find out the more accurate value of gradability, which is given by sine alpha. So these are the first two parameters: how much is the maximum speed and how much is the gradability, that is how much is the inclination the vehicle can go through. So that is nothing but called as gradability. Last one is acceleration. So what can be the maximum acceleration of the vehicle? So all this we have studied actually in the module 1 in the second part. The same formulas I am bringing here but with respect to EV. Now what is the definition of acceleration? So it is said that the acceleration performance of a vehicle is evaluated by the time it takes to accelerate the vehicle from 0 speed to 100 kilometer per hour. So this is a very important thing. That means from 0 to 100 kilometer per hour, in how much time the vehicle attains that 100 kilometer per hour from 0 speed. That is actually is a measure of acceleration of the vehicle. So for such cars or passenger cars, which is saying that it is performance, this performance is more important than maximum cruising speed and gradability. So whenever I am saying passenger cars and all, they don't run with 300 400 kilometer per hour. They run maximum with 120 130 kilometer per hour, we know that. Okay, so in that case maximum speed is not too high, and gradability is not very high because these vehicles are not used for very special applications of going through the hill and other things. So they are mainly a regular application. Okay, so maybe for 1,000 kilometer or maximum 500 800 kilometers tour and all those things we are using, or maybe driving in the city or driving through the highway. This is actually the passenger cars. So in that case this acceleration characteristic is very important than the cruising speed and gradability. So since it is the acceleration requirement rather than the maximum cruising speed and gradability that dictate the power rating of the motor drive, because acceleration is actually dictating what should be the power requirement of the motor. And for electric vehicle, the motor power requirement and how much power battery can supply, these two are the very important or most important parameters. I will repeat: for electric vehicle, how much power the electric motor requires and how much maximum energy the battery can supply, these two are the very important parameters. Hence acceleration, so acceleration is directly telling us that how much is the power required by the motor. Okay, at any maximum cruising speed. So that's why acceleration characteristic is very important in vehicle performance. So what we are finding is the acceleration time ta, that is from 0 to 100 kilometer per hour, is given by delta m divided by 2pt, and this is also a rough formula. This is not a very accurate formula. Vf and vb. What is vf and vb? We know vb is the base speed. So for every vehicle, if it's a 2-gear system, 1-gear system, 3-gear system, for every gear we know how much is the base speed. So that is vb. Vf is the final acceleration speed. So how much is the maximum speed of the vehicle is given by vb and vf. Okay, m is the mass of the vehicle, pt is the tractive power. So ft is the tractive energy, pt is the tractive power, energy divided by time is equal to power. So PT is the tractive power on the driven wheels transmitted from the traction motor corresponding to the vehicle base speed. So at VB, we are finding how much is PT. And M is the mass of the vehicle, delta is the vehicle rotational inertia constant. That means whenever the vehicle is converting the rotary energy into linear energy, so there is a translation. Okay, so in that case, conversion of rotary into linear is generating a term or which is called as the rotational inertia constant, that is given by delta. So this is actually a coarse formula, a rough formula of calculating how much will be the time taken by the passenger car to accelerate from, to increase the speed from 0 kilometer per hour to 100 kilometer per hour. But this is I told you this is a roughly calculated, not very accurate. So power rating obtained from PT equation is only the power consumed for vehicle acceleration. So to accurately determine the tractive power rating, the power consumed in the overcoming of rolling resistance and dynamic drag should be considered. So in this, whatever we are considering in this PT equation, whatever we are considering is only how much is the power required to increase the speed. But there are certain negative forces, there are certain drags. What are those drags? One is the rolling resistance, capital Fr. Another is the dynamic drag, aerodynamic drag, Fw. So if we incorporate those things into this equation PT, then the equation becomes little big. And the total tractive power for accelerating the vehicle from 0 to Vf, that means Vb to Vf in ta seconds, can be accurately obtained with a given formula. So initially we are only taking this part, that is delta m by 2ta. Here also we have seen delta m by 2ta, Vf square plus Vb square, like this. But this term, this is nothing but the rolling resistance term, and this is nothing but the aerodynamics drag. So this is actually, these two terms are actually negative term. So this is capital Fr, this is capital Fw. So if you just want the tractive part, how much power we are generating to take the vehicle forward, okay, that is this much part. There is a power. But how much power is giving me the opposition? So though these values are quite small compared to this part, first part, second and third things are very small compared to the first part. But then also, if you want an accurate formula, then you have to consider these two things into consideration. Now, above equation indicates that for a given acceleration performance, so this is the power required for traction. For a given acceleration performance, low vehicle base speed will result in a small motor power rating. Okay, so VB, if it is less, then motor power rating will be less. Differentiating the equation. So now something else we are trying to find out. We are differentiating this PT with respect to VB. That means how much is the power relation with respect to the base speed. That is what something we are trying to find out. And while we are trying to find out, what we have to do is dpt by dvb. So base speed is a very important thing for any vehicle. That means still how much speed initially its torque will be kept constant. Okay, that means when I have to shift the gear from the first gear to second gear, how much maximum speed I can get in the first gear. So that is the thing which is called as base speed. So what you have to do is now dpt divided by dvb if you are doing it. So the second term, third term, they are not having any base speed term, so they directly will go to zero. Now if you are above equation indicates that for a given acceleration performance, low vehicle speed will result in small motor power rating. So this is actually the relationship between vb and pt. Okay, and hence this is the way vb is dictating how much is the motor power. So low vehicle base speed, that means if vb is low, in that case motor power rating requirement also will be low. So differentiating this pt equation with respect to vb, we find that means only the first term is differentiated. So delta m into 2vb divided by 2ta, so it will be delta m vb divided by ta. So this is what you are finding, delta m vb divided by ta. So this m is actually given as mv. Okay, that means this is the rotational linear vehicle speed that we are talking about. So this is another thing, that is this line I can ask, and I can ask you to prove it. That is, prove that for low vehicle base speed, the small motor power rating will be resulted. So in that case, first you have to tell me what is meant by acceleration. In that case, you have to tell me what is TA, then what is PT equation. So this is PT equation with only F T and then you are supposed to find out what is ft net. This is the ft net, and ft net you have to say that it is having the positive power and the drags, so these two terms are negative actually. And then you are supposed to find out what is the power rating with respect to the base speed, so you are relating power with respect to the base speed. And from here you are finding out that if vb is less, in that case the pt also requirement will be less. Now from here we are finding that most important performance formula is this PT, and in actually this formula is having every term, and we gave quite a lot of time while we are doing the first module to derive this equation, if you remember. Okay, so this is another thing, this power rating versus the speed factor. So here you are finding how the PT is reducing. So PT is the actual tractive power which is taking the vehicle forward, and this is dpt dvb. So how the PT is changing with respect to VBB, this also you are finding here. So with respect to VB, what is the relationship of PT? That thing they have shown here. Then there is coming the next topic. So this actually finishes the second topic. With this slide, it finishes the second topic. So first topic was what are the different models of EV. We have seen there are 6 models. Second topic was what are the different performances. In the performance, third characteristic was, so in vehicle performance was the third thing. Before that, there was a tractive effort and all those things. And third performance was three vehicle performance. First one is speed. Second one is gradability. That means how much inclination it can overcome. And third thing is this acceleration. And we found that acceleration is the most important characteristic for a passenger vehicle. Now we are coming to the third topic in the that is the first part of module 4. There is a tractive effort for normal driving EV, and I told you it's a very interesting topic. So those who can stay back after 10:55, you stay back because you are having lectures, other lectures at 10:55. So I will continue. I will record this and I'll upload. Please listen to that because I have to complete this. So there are around 5-6 slides after this, but there is a diagram. So that diagram I will try to explain in short. So the vehicle performance described or discussed so far dictates the vehicle capabilities with respect to the 3 parameters, that is speed, gradability, and acceleration, thus dictating the power capacity of the drivetrain. However, in normal driving condition, that means when the vehicle is in the city or on the highway, these are normal driving conditions, maximum capabilities are rarely used. So how much is maximum speed? How much is maximum acceleration? They are generally not seen when the vehicle is running through the city or driving through the highway. So during most of the operational time, the powertrain operates with partial load. So it is not running with maximum speed or maximum acceleration when it is running through the city. So actual tractive effort or actual tractive power and the vehicle speed vary widely with different operating conditions such as acceleration, deceleration, uphill, downhill motion, and so on. So these variations are associated with the traffic environment, very important. So whenever we are on highway, traffic is less dense. Whenever we are inside the city, traffic is heavily dense. So the variation in the tractive effort, this is a function of how much is the traffic condition. City and highway traffic conditions vary greatly. So highway and inside city, these are the two opposite conditions. So as do the different missions of the vehicles such as passenger cars, vehicle with regular operation, and other schedules. So what you're finding is the tractive effort for normal driving EV. Okay, so these are some of the different schedules or urban cycle, highway cycle, and US 06. So these are different cycles. Okay, that we have taken as a case here, and we have found how much is the tractive effort for every of this case. So it is difficult to describe tractive effort for vehicle speed variations in all traffic environments, but then also some of them are captured. However, some representative driving cycles, so these are different standard driving cycles in New York, that is captured. So they have been taken to emulate the typical traffic environments. These driving cycles are represented by the vehicle speed versus operating time while driving on a flat road, and some typical driving conditions are this. Now here there's a graph where acceleration is being consumed constant with a short period of time. So within how much time, how much is the increment in the velocity that we are finding. Okay, so this is another graph, so time versus speed graph. So at different tractive conditions, how the vehicle speed is varying within how much time. So speed versus time is actually acceleration. So here actually this dv divided by dt is giving me acceleration. So this is a deceleration part, This is the acceleration part, and in this acceleration part also you are finding that initial part acceleration is very high, and in this part acceleration is little low, and this part is deceleration. So this is actually acceleration with respect to time curve, or velocity change with respect to time curve and all. So in a short time period, the speed is assumed to be linear with time. So this is called piecewise linear graph, and acceleration is constant as shown in above figure. So if you're finding the velocity is changing linearly, that means acceleration is also constant within this period. So this ramp, if you differentiate it, you're going to find this is a step kind of a thing. So the step is nothing but the amplitude of the acceleration. So the acceleration dvdt in the driving cycle can be obtained by the formula, so dv by dt. So how to find the acceleration from this speed formula or velocity formula? We know this. So v2 minus v1 divided by t2 minus t1, which is given here. And what is the formula for finding how much is the tractive effort? That is given by ft. So previous formula, it was the formula for power. If you multiply by that by time, you are going to get the energy. So this is ft. Previous slide we had shown pt. So tractive effort in any instant in the driving cycle can be calculated using this formula. So this is actually tractive force. Previously I had given you the tractive power. Okay, and the relationship between force and power is force divided by time is equal to power. So either you remember that pt formula or you remember ft formula, anything will do. Understand this. Okay, so there are four graphs which I have shown. So this is the main thing. This is the first case. Here you are finding that the vehicle is starting, stopping, starting, stopping like anything. Okay, so please give me some 2 minutes time. This is the most important thing, and you can define this kind of thing and explain. So what is this? This is called ftp 75 urban. That means the vehicle is running through the city, and you are finding that how many times it is starting, stopping, starting, stopping and all. And you are finding that first gear is this, second gear is this, there's a third gear, so there's a multi-gear operating time, and plus means where your vehicle is as far as speed is concerned. So what you are finding is hardly you are in this third gear. That means hardly you are in this 80 kilometer per hour speed. So most of the time you are rotating within this 0 to 40 45 kilometer per hour speed. So this is very much relevant if those who know how to drive the vehicle. So whenever you are within the city, you are always in the first gear and maximum in the second gear. You cannot take it into the third gear. So that's why plus signs are less here. First and second gear most of the time you are in. That means you are in this first gear or second gear operation, and your vehicle speed is within this 0 to 40 45 region. Second case, just see your highway. So this is ftp 75 highway, and your vehicle is running with almost 100 kilometer per hour speed. In this case only once you had gone to 80 kilometer per hour, so y-axis is speed here, and most of the time you are in 40 45 kilometer range. But in this highway you are finding that you are most of the time at 100 kilometer per hour range. So most of the plus signs are here. So mostly you are in third gear or fourth gear, and you are in highway because you are most of the time you are in very high speed. So very smoothly you have started the car, very smoothly you have changed the gear from first gear to second gear to third gear, and most of the time you are in third gear fourth gear thing. That's why your vehicle speed is very high, around 100 kilometer per hour or so, because this is ftp 75 highway. The previous one was ftp 75 urban. Please go to the book, you will understand. Now this is another case where it's a mixture. So us06, here you are city in initial part, you are in city for latter part, and in between maybe you are in kind of a highway kind of a thing. So here you are finding that speed is around 50 60 or 100. So everything is there. So because of this range, that is from time of 120 second up to 500 second, you are passing through highway. So in that case your speed is here, so around 80 to 150 kilometer per hour. Okay, and whenever you are in initial phase, that is the first 0 to 120 seconds or so, you are in the first gear second gear. And whenever you are here, that is 500 to 600 seconds. That means this is actually a 10-minute cycle whichever is shown. So whenever you are here 500 to 600, again you are in the first gear or second gear. So first one diagram, this was only you are in first gear second gear. Second one diagram, you are only in third gear fourth gear, and this third diagram is actually a mixture of both. So for the first period and the last period, you are in first gear second gear, and in middle this is the highway kind of thing. So you are having higher gears, that is the third or fourth gear. And there is another diagram, you are finding that this is J227A. This is a special case actually. Here you cannot increase the speed of the vehicle too much, so your maximum speed is C, around 30 35 kilometers. So that's why you are totally within this first gear. So no need to increase the gear because your maximum vehicle speed is 30, 35, 40 kilometer per hour. So whenever the people are learning the driving, at that time their driving characteristic is like this, because they are driving only with first gear or second gear. Whenever people are learning how to drive, they cannot increase the speed beyond 30, 40 kilometer per hour, or they generally don't increase to third gear, fourth gear. Okay, so they generally restrict themselves to first gear, second gear, and all. So this is what the characteristic we are finding. So in this case, you are finding it's a wide range of power, wide range of speed. But in the first case, the power range is also very limited, and the gear range is also we are in the starting part. So this is actually the second. These are actually the four characteristics what we are finding: mixture of speed. So first gear, second gear, and higher gear. So these four are very important characteristic that you can find. So this is the last topic. So I will complete it. There are only 2-3 slides. I will do that. So if you want to leave, you can leave. Another 5 minutes of discussion required. I will do that. So in transportation, the unit of energy is usually kilowatt hour rather than joule or kilojoule. So kilowatt hour is generally the standard unit for energy. The energy consumption per unit distance. This is actually taken as a measure of EV. So how much is the kilowatt hour for every kilometer? This is the measure of evaluate the vehicle energy conversion consumption. ICE vehicles, that is the petrol driven vehicles, are the most commonly used unit is a physical unit of fuel volume per unit distance, that is 100 kilometer. That means how much amount of petrol or diesel is giving how much kilometer. That is the efficiency, or that is the fuel efficiency, that is the energy consumption. In the United States, the distance per unit volume of fuel is usually used. This is expressed as miles per gallon. So in our country, it is kilometer per liter. In US, it is miles per gallon, and they call it gas or gasoline. Okay, the battery powered EV, the original energy consumption unit in kilowatt hour. So remember this. What is the unit of energy consumption of electrical vehicle? It is kilowatt hour per kilometer. That means 1 किलोमीटर जाने में कितना किलोवाट आवर एनर्जी लग रहा है इलेक्ट्रिकली. So that is actually the unit of energy in case of electric vehicles. So in our country, actually it is or everywhere EV is given in kilowatt hour per kilometer. So there's a measure of battery terminals, and the battery energy capacity is usually measured in kilowatt hour, and the driving range per battery charge can be easily calculated. So this is another unit of energy consumption. That means if I charge it fully once, like once I fill up the tank totally, how far can I go? That is for the this gasoline based or petrol based vehicle. So likewise in electrical vehicle, if I charge it once completely in one charge, how far it can go, that is actually a measure of energy consumption of the vehicle. So similar to ICE vehicles, 1/100 kilometer for liquid fuels, or kg per 100 kilometer for gas fuels such as hydrogen, or mpg per miles. Mpg means miles per gallon. So is a more suitable unit of measurement for vehicles that use gaseous fuels. So this slide is talking nothing but the different units that is used for energy consumption. So energy consumption is an integration of the power output of the battery terminals. For propelling, the battery power output is equal to the resistance power and power losses in the transmission and the motor drive. So I'll tell you that this formula we have done quite a lot of times. So here FR plus I. So what is FR? FR is nothing but the rolling resistance, and I is nothing but the gradability. This is also the resistance. So mg into FR plus I. This is nothing but some resistance kind of a thing. Plus half rho A, CD, AF, we have all the same. So the CD is a drag coefficient, AF is the area of the front, area of the curve. So this first two terms, okay, so this PB out, okay, what is the PB out? How much is the output power? So just go through this. So for propelling, that means taking the car ahead, the battery power output is equal to the resistance power and power losses in the transmission and the motor drive, including power losses in the electronics. Okay, so power loss in the electronics is not shown here. So for running the running the light, maybe AC and other thing, that is also in some losses. So yesterday's lecture we have seen, so there was some hoteling kind of loss there, hotel environment loss. Okay, that is not shown here. So here only we have shown as gradability, rolling resistance, and this is the aerodynamic resistance. So these two terms are actually negative term, and this is m delta dv dt. This is nothing but the power, which is nothing but the energy, which sorry, this is the power because dv dt is there. So this is nothing but the power for traction. So So this is the power which is taking the or which is propelling the vehicle, and these are the negatives. Okay, so these two terms should be negative. And PB out is equal to V by eta T eta M. All these things are efficiencies likewise. So for propelling, the battery power output is equal to the resistance power and power losses in the transmission and the motor drive. So that is this part. Okay, so these are the losses, including the power losses in the electronics. So electronic power loss is not shown here. The power losses in transmission and motor drive are represented by their efficiencies eta T and eta M respectively. Thus, the battery power output can be expressed as, so this is the battery power output. So actually we should show it like this: M delta dV dt minus this minus this. Okay, so these two terms are negative, that you have to understand. So here the non-traction load or auxiliary load is not included. Auxiliary load means those things, that is running the AC, running the light and all those things. So in some cases the auxiliary loads may be too significant to be ignored and should be added to the traction load. So auxiliary load can be AC. So that's why while starting the car, certain times we stop the AC. So when regenerative braking is effective on the EV, a part of the braking energy wasted in the conventional vehicle can be recovered by operating the motor drive as a generator and restoring it into the batteries. So the regenerative braking power at the battery terminal can be represented as. So this is actually the input power to the vehicle, and the top one is actually the output power to the vehicle. So in this case, there is coming a term as alpha. Okay, so this is alpha into V divided by ET/EM. So PB in and PB out, only difference is alpha. Okay, so alpha is a coefficient, and we will find the regenerative braking factor alpha. So you see the previous two things. This is the output power, and this is the input power during regenerative braking. So whatever terms are there in case of output power, the same terms are there in case of input regenerative braking power as well, only it is multiplied by a function of alpha. So what is alpha? Alpha is the regenerative braking factor. So maybe 0.1, 0.2 or something. So it is a function of the applied braking strength and the design and control of the braking system, which will be discussed in detail in the later chapters, because we have seen already this thing, because we have already studied regenerative braking. So the net energy consumption from the batteries are, so that is nothing but traction power PB out plus braking PB in. So whatever power we are giving, that power is doing two things. One is actually it is so whatever braking power we are generating, it is doing two things. One is braking the vehicle, and second one is generating a regenerative braking. So that regenerative braking and output power, this is actual E out of the system. So here you are finding that it should be noted that the braking power PB in has a negative sign. So that is what I told you. When the net battery energy consumption reaches to the total energy in the battery measured at the terminal, the traveling distance between two charges, usually called as effective travel range. So this is very important, that once you have charged the vehicle, how far it can go, that thing is called as effective travel range. So the traveling distance between two charges or effective travel range is determined by the total energy carried by the batteries. So after one charge, how much the energy the batteries are carrying, the resistance power and the effectiveness of the regenerative braking. So these are three very important things. That is the traveling distance between two charges is determined by the total energy carried by the batteries. That means how much charge we have given. Resistance power, so resistance power are different. So this Mg FR Fi is a resistance, this is also a resistance, and whatever auxiliary usage are there, that is also a resistance. And the effectiveness of the regenerative braking. So regenerative braking is continuously charging and other things are actually dissipating. Okay. So here there's an energy consumption curve or energy consumption graph, which we call as the electric motor efficiency characteristics with respect to speed. So there's a motor torque and this is the motor speed. So efficiency of a traction motor varies with its operating point on the speed torque plane as shown in the figure. Okay, so this is a curve which is showing actually the speed torque. So y-axis is the torque, x-axis is the speed, and we are finding that different efficiencies which are mentioned in this. So here the most efficient operating area exists. In powertrain design, this area should overlap or at least be as close as possible to the area of the greatest operation as the mentioned in the previous section. So what you are finding is, just see what we are finding. So x-axis is the motor speed. Motor speed is nothing but how fast the electric motor is rotating. Okay, so here I told you that electric motor rotates almost up to 6,000 rpm. So here the motor maximum efficiency, this is the region. This is the region where efficiency, what you are finding is it is a maximum. So typical electric motor efficiency. So we should not think that whenever we are driving the vehicle with higher speed, the vehicle is giving me maximum efficiency. Okay, so what is meant by efficiency? Efficiency is how much energy you are putting to the vehicle and how much energy you are getting as the output. So energy putting to drive the car, okay, and that has to overcome a lot of losses. So there are mainly three kinds of losses we know. First one is the gradability loss, that means inclination is there. Then there is the frictional loss, that is there. Then there is the aerodynamic loss. So these were the three losses we learned. There is another fourth auxiliary losses we are finding, that is all the AC and the lights and the video, audio, all those things are there. So they are called as auxiliary electrical loss. So all those losses, if you subtract from the tractive force, whatever energy is remaining, that is actually used to propel the vehicle further in front. Okay, so always we are driving the car fast does not mean that efficiency is higher. Here you are finding that you can drive the car maximum up to 5000 rpm. Okay, so this 5000 rpm may be around 250 kilometer per hour or 200 kilometer per hour. So that is, I'm talking about V. Here I'm talking about N is nothing but the rotational speed of the motor. Okay, so whatever it is, V or N, whatever you call it, but you are finding that whenever the motor speed is in the range of 1000 to 1500, okay, so this is almost 30% of the maximum speed. So Vmax into zero point 0.3 or 30% of the maximum speed. Within that, we are finding that the vehicle motor can generate maximum almost 375 it can generate almost 375 Newton meter torque. But here you are finding that for maximum efficiency, the torque is around 220 or 230. So this is the range around 120, 130 to up to 220, 230. So this is the range for maximum efficiency motor torque, and the speed range is 1000 to 1500 rpm. So that means what we are finding is, if we can find out the sweet spot. What is the sweet spot? That is, we have to drive the car, if it can go maximum up to 200 kilometer per hour, we can drive the car within maybe around 50 to 70 kilometer per hour. Okay, so from this range we can find that. So this 0 to 5000 we can grade between 0 to 200 kilometer per hour. So almost 20 to 30% of that. So 20 to 30% of maximum speed. That means 200 ka 20 to 30%. That is around 40 to 60 70 kilometer per hour. If we can drive the range with that speed, then only we are going to get maximum fuel efficiency. So this is a very important thing, because this is going to increase the lifetime of your engine. This is going to increase the battery efficiency. This is going to increase the lifetime of the battery. This is going to give us maximum fuel efficiency. That means in one charge, how maximum distance you can go, that depends on in which speed you are driving the vehicle. So what we are finding is, if we are driving the vehicle around 20 to 25, 30, around 30 kilometer percent of the maximum speed. So 5000 ka 20 or 30%. That means if you are saying 0 to 200 kilometer, uska 20 to 30%. That means around 40 to 60, 65 kilometer per hour. So for a maximum speed of 200 kilometer per hour, if you are driving the vehicle with a speed of 40 to 60 kilometer per hour, that means we should have control over ourselves. I can drive the vehicle up to 200 kilometer per hour, but I will be losing the efficiency at that time. That means whatever energy is going, so in that case efficiency is only 60%. That means in one charge you cannot go maximum distance. Okay, so if your aim is that in one charge I will go maximum distance, in that case you have to drive the vehicle with 20 to 30% speed of the maximum speed. Okay, so in that case you can go almost 90% efficiency from the vehicle. So you can see this is a contour kind of a thing. So you are increasing the speed means your efficiency, that is fuel efficiency what you call, or battery efficiency, energy usage efficiency, that is going to reduce. So this is a very important slide. This also you should remember, and if asked, you should produce a prototype in the exam. And here also there are two range. So this is the constant torque range, and after that the torque is falling. The right side is the constant power range. Okay, so if we are within the constant torque range and we can drive the vehicle with 20 to 30% of the maximum speed, then we are going to get maximum battery efficiency. Battery life will increase, the maximum efficiency we can obtain from the vehicle. Okay, so this was what I wanted to tell you. So this completes the first part, that is the part A of module 4. We will start with the second part of module 4, that is EHV. Okay, that is hybrid electric vehicle.